Hi, my name is Chris Regal, and today I'm going to walk you through some R code that I wrote as part of my master's for cybersecurity and data analytics coursework at Western Kentucky University. So my first task is to upload some body measurements into R and use it to make predictions for body fat. I import the data here. I see that none of it is categorical, and it appears to be randomly assembled. Therefore, I'm going to create a training data set and a validation data set, 80 and 20%, 202 versus 50 observations, 202 in the training, 50 in the validation. I'm going to use a linear regression because I'm predicting a continuous numeric variable of body fat. Body fat's our target variable using all other variables, and the data I'm going to train my model with is going to be that 80% training data. Next, I'm going to make the linear predictions using the predict function of my linear regression model, except now I'm making the predictions using the validation data. The model's been trained using the training data. Now it's going to make predictions using data it hasn't seen yet. There are the predictions. In order to assess the accuracy of my model, I'm going to compute the root mean squared error. So the root mean squared error, when I run this computation, is going to give me a root mean squared error of 0.844, rounded of course, and that is going to show that my model is only 0.8 of a percentage point off from the actual values. And if I run a summary, I see that my R squared values here show high levels of accuracy at 0.97 or 97% accuracy. Second model I chose to make these predictions was a regression tree, again predicting a continuous numeric variable. I'm going to run the library R part to make sure that the R part package is installed so that I can actually generate a regression tree. This regression tree is so named. I'm going to use R part to again target body fat using all other variables. Training data is what I'm training the model with, and my method is going to be ANOVA, telling R to create a regression tree as opposed to a classification tree. Next, for my predictions, I use the predict function to make my predictions, or to have my model make predictions now, again, using the validation data, type being vector for continuous, or to specify the output that I want. There are the predictions seen on the right. I again compute the root mean squared error for this model, and I get 2.35 rounded. That means that my linear regression model is going to be significantly more accurate than my regression tree, as my regression tree is 2.35 percentage points off, and my linear regression model is 0.8. And if I run a summary, I see the raw statistics from the model. And that is my body measurements. For loan applications, if I clear this out for clarity, I import loan application data set, and I see we have lots of categorical data. We have 8 variables that are categorical, but again, the data is assembled in no particular order. So I'm going to use the first 8 lines of code here to tell R, using this factor function, to tell R to treat those variables as categorical and not just raw text. Again, I'm going to split the data into a training set and a validation set using an 80% and 20% split. For creating the model, I'm going to use the GLM function. My target now is loan results, so I'm trying to predict whether someone is or is not approved for a loan. So loan result tilde period, telling R to use the rest of the variables. The data, again, is going to be training data. Family is going to be binomial because I want a yes or a no, aka a 1 or a 0, that we will translate later as my output. There is my model. If I run the summary of my logistic regression, of note, I get my p-values here, and I see that credit history has a high level of significance, significantly higher level of significance than any other predictor. Now, when I run I'm going to call this predicted probabilities. I'm going to use the predict function to have my model now use the validation data, give us a response and actually make predictions is that are the people in the validation data going to be approved or disapproved for a loan? There's the raw predictions. For classifying, I use the if-else function to take these raw probabilities or these raw predictions we see on the right, and if those raw predictions are greater than 0.5 or equal to 0.5, they'll be approved for the loan, so they'll be given a yes, and if they're below, they'll be given a no and disapproved for the loan. As we can see, 0.7 yes, 0.16 no, and so on and so forth. Finally, I'm going to print as accuracy is the sum of the predicted class, so basically the sum of all of the correct predictions from the model divided by, in the validation data set, divided by all of the applications in all the applicants in the validation data set, gives this model an accuracy of 83% or 0.833 repeated. Again, categorical prediction. So the second model I'm going to run is going to be a classification tree. Again, I install RPart I run the library RPart to ensure the RPart package is installed. I then create a classification tree using RPart with the target variable of loan result and using all variables. I'm going to train the model with the training data and now using method of class to tell R that this is a classification tree as opposed to the regression tree that I used in the previous data set. There is our classification tree. Back again, there's our classification tree. I now use the classification tree to make a prediction using the validation data set, again, making our with classifications. There's my predictions. And finally, I use the same print function accuracy is to get the accuracy of the model, and I get 0.833 again, 83%. Why? Why are they so similar? Because if we look back, this credit history is such a strong predictor that it is affecting the data in such a way that both models are going to give us similar accuracy because it has such a strong effect on whether someone does or does not get approved for a loan. All right, this has been the code that I've built to make predictions. Thank you very much for listening, and welcome any feedback. Thank you.